Today, we're going to finish up the chapter. But first, I want to review what we did last time. So here we have the quick review. What I want you to do here is find the number of positives, negatives, special solutions, not the actual ones, just the number of them, and then find me all possible zeros. And if you think about it, both of these were covered under special terms. The number of positives and negatives, what rule do we use to find those? Yep. Descartes' rule of signs. All it does is look at sign changes from the first to the second, second to the third, third to the fourth. And all possible zeros, what was that called? Yep, very good. Rational zero theorem. And that formula was P over Q, or all the possible factors. So, here we got this written down. Let's begin. Positive solutions. Yeah, what we have to do is we start off with a positive, we go to a negative. That's a sign change. From negative to positive, that's a sign change. From positive to negative, that's a sign change. So add those up. We get 3. So the number of positive solutions is 3 or 1. Why is it 3 or 1? Which similar ones? You're close, very close. Yeah. Okay. Yeah. So you're on the right track. If it's not positive or negative, if it's not integers, then it's either imaginary or radicals. And remember, imaginary and radicals always have to have a conjugate pair, so they have to come in 2s. So that's why I subtract 2. So the number of negative solutions, I gotta first put a negative x in the function. So anywhere I see an x, I put a negative x. Now, the only ones we have to worry about are the odd exponents. If the exponent is odd, that negative multiplies by the sign in front of the coefficient. So positive times negative is negative. If it's even, don't worry about it. Just erase that negative sign inside parentheses. This one has a 1, so that's odd. So that negative, negative times positive is negative. So how many sign changes? Nope. 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 Good morning. So there are no negative solutions. But how many solutions are we supposed to have? So we'll look at these. The possibilities we have is this: 0 as a solution. What's the only way that 0 can be a solution to a polynomial? A 0 is a possible is if each term has an x. In other words, there's no constant terms. But we have a constant, so we can't have any of those. Number of positives. We saw we had 3 sign changes, so it's either 3 or 0. Right. Again, you can't have any zeros. How many negatives are there? 0. So there's none. So that means, remember, here the degree is 5. So we have to have 5 answers total. This is the 5th order polynomial. Vertically, 0 plus 3 plus 0, what do we need here? Because it has to equal 5. And specials are imaginary or radicals. They have to come in conjugate pairs. So how about the other one? I'm sorry, it wasn't 0, it was 1. It was 3 or 1, I'm sorry. 0 plus 1 plus 0, we're missing how many? 4. So this tells us the possible combinations of our solutions. So this tells us, this chart here tells me the possible number of positives, negatives, and specials, all by the sign changes. All right. Any questions? That was the first question. That was the first problem. The second one said, from this polynomial, find all of the possible zeros. How do we do that? The P over Q, rational zeros. The leading coefficient is Q. The constant is P. Why don't I put plus or minus in both of those? Because we don't know what the signs are. They could both be positive, they could both be negative, they could be opposites. So once we figure out what the P and the Q values are, we have to take their factors. What are all the possible factors of 4? One times 4 is 4. 2 times 2 is 4. Those are all the possible factors of 4. And the possible factors of 2 are 1 and 2. So factorize P and Q. Everybody okay so far? Did I lose anybody? Okay, so now, once we figure out these, we know there's 3 on top. 3 times 2 is 6. We're going to have 6 plus or minus answers. We first, all of these top numbers over 1. So we have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1. That's over the 1 on the denominator. Now we got to do it for the 2. Plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 4 over 2. So there are my 6 possibilities. 2 times 3. Now let's go and work out the fractions. Something else would happen. 1 divided by 1 is 1. 2 divided by 1 is 2. Where did I get 3 from? That should be 4. It should be 4 over 1, I'm sorry. 4 divided by 1 is 4. And then 1 over 2. 2 over 2 is 1, but we already have 1, so we don't have to worry about this one. 4 divided by 2 is 2. We already have that, so we don't have to worry about that. So we've dropped down to 8 possible answers. Can we go any further and knock out some more we don't need? Remember the rule of signs. How many negatives do we have? Look at your sheet. How many negative answers do we have? 0. So we know there's no negative solutions, so we can get rid of all the negatives. So our possible answers are these. All the positive ones we would try. So that means, according to our table here, we can have 3 of these could be the answer and we'll have 2 special ones at the end. Or only 1 of these will work and we'll have 4 special ones. So we narrowed down our possibilities from infinity to these 4. That's how it works. So that's a review from last time. That's what we did last time. Again, the videos are out already. I sent them to y'all a couple weeks ago. Here we are today. Section 5. Rational functions. We're going to talk about the domains and the graphs. And since we have rational, which are fractions, we're going to have what are called asymptotes. We'll talk about that in a second. So and there are 3 asymptotes. There's a vertical, horizontal, and oblique. You can only use one of, you cannot have an oblique and a horizontal at the same time. You can have one or the other, or neither of them. A function doesn't need to have a horizontal or an oblique asymptote. And we'll talk about why in a minute. In other words, you cannot have one of each of these at the same time. You can only have one of them at a time. only use one of these at a time. So when we talk about rational functions, we talk about one polynomial on top of another polynomial. The only rule we have is that the bottom polynomial cannot equal 0. So let's look at this example here. Polynomials, to begin with, have a domain of negative infinity to positive infinity. That's a regular domain of a polynomial. Since we have a fraction, that changes. Look at this one. Are there any values we cannot use? Look at this box. What does it tell you? The bottom number cannot equal 0. If it's 0 on the bottom, it's undefined. So what do we do with that x minus 3 number? Set it equals 0 and solve for x. So since if x equals 3, the bottom is 0. We cannot have that. So we cannot use 3 as an answer. That is what we call a vertical asymptote. A vertical asymptote is an x value that makes the denominator equal 0. There are restrictions of our domain. So what we say here is the vertical asymptote is 3. Since 3 is our vertical asymptote, we can't use that. We have a vertical line right here that the graph cannot cross. Since we cannot use 3, there's a block, a wall that the graph cannot cross. That's a vertical asymptote. So with this restriction, what's my domain? Remember, it used to be negative infinity to positive infinity. What is it now? What's that? Negative infinity, oops, to 3. Anywhere else? So we can use x's here. Anywhere else? How about on the other side? We can use anything there too. From 3 to positive infinity. There's my new domain. So we use set notations to determine what our intervals of our domain are. What's my vertical asymptote here? Yep, it's 0. Because what do we do whenever we have a fraction? Set the bottom equal to 0. So x equals 0, as far as we can go. So the vertical asymptote is 0, which means, this means that we cannot use the x value of 0. So our domain is negative infinity to 0, and from 0 to positive infinity. How about if I gave you something like this? What's the first thing you have to do after writing it down? Your first step is always to factor the numerator and denominator to see if anything can cancel out. So the bottom, what signs go in there? We know the signs are, the first terms are x, because that's the middle term. That goes in the middle right there. What signs go in there? Where do we get, what hint, what gives us a hint in the equation? The second sign. Since the second sign is minus, that means we have opposite signs. And the first sign tells us that the bigger answer gets that sign. So now we gotta figure out what numbers. What times what equals 2 when we subtract them? It equals the coefficient of the middle term, 1. Yep. 2 times 1, 2 minus 1. And since 2 is bigger, it gets the negative. So 2 goes there, 1 goes there. Nothing cancels. So what are my vertical asymptotes? It's always the opposite signs. -1 and 2. Because remember, you're supposed to take and make them equal to 0. So my domain then if you look at the graph, I have at -1, I have a vertical asymptote at -1. And at 2, I have a vertical asymptote. So let's see what I can use. I can use this part, which is from -infinity to -1. Or I can use these numbers from -1 to 2. Or I can use these numbers from 2 to infinity. All right. Let's do one more. Well, no, let's make this a minus. I'll make it easier for you, because if we had the other one, something would cancel, and that's another discussion for later. So the first thing you have to do is factor them out. So again, the top, we have X and X. What signs go up there? Yeah, because the second signs are minus, they're opposite signs. What times what is 3? When you subtract them, you get 2. 3 and 1. 3 times 1 is 3, 3 minus 1. And so the 3 gets the plus sign since it's bigger. Same in the bottom. Since the second signs are minus, they're opposite signs. What times what is 2? When you subtract them, you get 1. 2 and 1. 2 gets the negative. Since nothing cancels, what are my vertical asymptotes? Very good. It's always the opposite of what's inside the parentheses. And if you don't see that, set them equal to 0 and work them out. So at -1, we have an asymptote, and at 2, we have an asymptote. So the domain is from -infinity to 1, or -1, from -1 to 2, and then from 2 to positive infinity. And we have the union between them. So that's the vertical asymptote. Set the bottom equals 0 and factor it out and solve it. Horizontal asymptotes, which I'll call HAs from now on. Horizontal asymptotes depend on the degree of the leading terms of the numerator, that's the top number, and the denominator. That's the bottom number. So horizontal asymptotes depend on the degrees of the numerator and denominator. It's redundant to say it's the leading term, but yes, but that's what's very important. So let's say we had our polynomial, a rational polynomial. The top would look something like this. Yeah, and that's how we defined a polynomial when we first talked about it. And the bottom would look like this. All this says is the exponents are decreasing. If it was 5, then it's 4, 3, 2, 1, 0. So that's all it says is the polynomials are set up in a decreasing order. So according to our rule, the horizontal asymptote depends on the leading terms only. All this other stuff I can get rid of. I don't need it for this part. I simply, I don't even need that part. The exponents are the important parts. Those are the degrees. 3 things can happen. For each of these examples here, we're going to be looking at as x gets bigger, as x goes to positive infinity. So the first one, 1 over x. As x gets bigger, where does this number go to? Where does it approach? One over 1, 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000. What's happening to the number? 1 over 100 is small. No. As x gets bigger. So as x gets bigger, as the bottom number gets bigger, what happens to the overall number? It gets smaller, eventually approaching 0. We know the graph. This was this graph. So as x goes to infinity, the graph itself gets lower and lower and lower, but never touches the x-axis. So it approaches 0. How about if we have this equation and x gets larger and larger and larger? What happens? This is basic math, everybody. Just look at this. What happens? What can you do there? Anything mathematical? Really, you don't see what you can. Can you cancel anything? It's a fraction. Is there anything same on top and bottom? The x. You can cancel the x out. You're just left with the coefficients, a number. What that means, since this is a number, it's a line that goes through there at A over B. How about this one? As x gets larger, what happens to that number? Yeah, and as x goes to infinity, this one goes to where? Because this function looks like that. Remember, we're talking about horizontal asymptotes. So if there's more x's on the bottom than the top, your horizontal asymptote is 0. That means where y equals 0. The horizontal asymptote goes through the y-axis, which is the x-axis in this case. Where y equals 0, that is your horizontal asymptote. You notice how the graph never touches it? If your x's are the same, they cancel. You're left with only what's on top, what's in front of them. That's a horizontal line through that point. And if there's more on top, you don't have one. So that's what happens pictorially, graphically. Let's see what that means mathematically. Remember, we're looking at an equation that looks like this. If m is bigger than n, in other words, if the bottom exponent is bigger than the top exponent, the horizontal asymptote equals 0. Because you have more x's on the bottom. If they equal, then your horizontal asymptote is simply the coefficients because the x's cancel. And if the bottom is smaller than the top, none. What's my horizontal asymptote here? Yep, because you have more x's on the bottom than the top. Okay, remember, only look at the leading term. This other stuff you can get rid of. Only look at the leading term. 2x over x squared. Since you have 1 on top, 2 on the bottom, they cancel. So we're left with more x's on the bottom. How about that one? Very good. -7/11. Because remember, all you're dealing with are the leading terms. This other stuff I can get rid of. I don't need for this part. And since x to the fourth cancels out, I have -7/11. How about this one? What's that? Very good. Why? Yeah, because get rid of everything that's not the leading term. We have 3x to the 5th over 7x to the 3rd. X's cancel, so we're left with 2 on top. So that's, just look at the leading terms. That's all you have to do for the horizontal asymptotes. No. None. Because there's more on top. You're right, there is no horizontal asymptote. But since the degree of the numerator is 1 more than the degree of the denominator, we have an oblique asymptote. Yes, typically if there's more on top than the bottom, it's no asymptote. But if the difference is by 1, then we have a slant asymptote. And it's a slant asymptote, if you want to call it that. It's not horizontal or vertical, it's a slant. Since the degree, so the numerator is x squared. The denominator is x. Since that is plus 1, then I can have an oblique asymptote. To find the oblique asymptote, To find the oblique asymptote, you use long division and remove any remainder. So remember, since I have an oblique asymptote, I take the denominator, put it on the outside, and the numerator on the inside. Remember, if you're missing a variable, put a 0 in its place. You have to have all the columns taken care of. So what times x gives me 2x squared? Yep, 2x. Now take this answer and multiply it to both of those. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Change the signs and add the 2x. The first term always has to disappear. 4 minus 3 is 1. Bring down everything else. Repeat the process. What times x equals x? Positive or negative? Positive, yes. So it's positive 1. You're thinking I'm giving you a trick question here. So we take whatever we have here, the plus 1, times both of these guys. So 1 times x is x. 1 times negative 2 is negative 2. Change the signs and add. 2 minus 1 is 1. There's your remainder. We don't use it. We don't need it. We only need that answer. Your oblique asymptote is that line. What does that line look like? Remember chapter 1? Linear equation, y equals mx plus b. You're always going to end up with a linear equation. That's the reason if you have more on top than the bottom by 1, you're always going to end up with 1x. Plot the y-intercept, then follow the slope. Up 2 over 1. Up 2 over 1. There's your vertical asymptote. I mean, your oblique asymptote. What's your vertical asymptote? What's your vertical asymptote of this equation? Yeah, 2. So at 2, we have a vertical line. This is where the graph gets really weird. Let's find our first point of this equation. Let's use, since 0 is not an asymptote, let's plug in 0. If we plug in 0, what do we get? We plug in 0, what do we get? Let me help you. If you remove all the x's, what do you get? Just erase them. -1 over -2, which is 1/2, which is right about there, which means our graph will look something like this. It'll stay within those lines. Actual graphing comes in the next section. All right, so that does it for section 5. Section 6. We're going to do 2 of them, polynomial inequalities and rational inequalities. This PI and RI, PIs. So let's look at one we have already. We know already what it looks like. As a general rule, polynomials in general, all polynomials, whenever you solve them, have to have 0 on one side. So whether it's polynomials or rational equations, you have to move everything to one side. Has 0, treat it like an equal sign. Set equals 0, these are your steps. Second step, factor it. We have x and x. The second sign's a plus. What does that mean? The signs are the same. They're the first sign, so they're both pluses. What times what is 6? When you add them, you get 5. 2 and 3. Solve for the x's. So x equals -2, x equals -3. These are what we call the critical values. So graph the equation. So we plot these 2 points at -2 and at -3. What's the rest of the graph going to look like? What kind of equation is it? What's that? Can't be linear. It's got a square on it. We have two answers. Linear equations only have one answer. So determine what's the degree of the equation. Degree is 2. It's the largest exponent. A degree 2 equation looks like what? It's a parabola, right? Since the leading coefficient is 1, it's positive, and that's greater than 0, it opens up. So we know the graph here looks something like this. That's the stuff we've been doing all along. Now let's look at the question. The question is asking us, this equation is greater than or equal to 0. Do we want the part of the graph that's above or below the x-axis? Since the equation is asking for this, it's greater, this equation is greater than 0. Is it above or below the x-axis? Above, because above the 0, above the x is the positive numbers, which are all greater than 0. So we only want the part of the graphs that satisfy those parts. So what's the answer? Well, the part of the graph that's above it is from negative infinity to negative 3, and then from 2 to positive infinity. The question here, do we include the dots or not? Is it a parenthesis or a bracket here at negative 3 and 2? It's equal to, so it's a bracket. And we have a union between there. So move everything to one side, factor the equation, find the critical values, plot them, sketch the graph, and look, if it's greater than, it's above, if it's less than, it's below. So make that nicer. X squared plus 3x minus 5 less than equal to x plus 3. Your first step is what? Set equals 0. So move everything to one side. Same as last. Put that phone away. No, oh, wait. It's, don't abuse the fact that I'm right now saying you can take the final exam at home. I can always just switch that. Always move the smaller to the larger. These are x, this is x squared. So everything has to go to the left. So we have x squared. 3 minus 1 is positive 2, negative, negative. 5 plus 3 is 8. We factored it. We solved it. So now we got to factor it. X and X. Since the second sign's a minus, the signs are different. What times what is 8 when you subtract them, you get 2? 4 and 2. Solve them. These are your critical values. So at negative 4 and 2. It's a quadratic equation, so both ends point the same direction. It's positive, so it points up. So the graph is like this. We only want the part that's less than 0. We're only interested in this part. From negative 4 to 2. We only want these x's. We want part of the graph that's below the x-axis. Since it's equal to, I use brackets. Any questions about this so far? We need to know this because the next part is rational inequalities, fractions. The last part of chapter 4. Rational inequalities, fractions. And same thing, since a polynomial has to have 0 on one side. Now you have to factor both the top and the bottom. You have to factor both parts and solve them. So we have P of X over Q of X. The top part set equal to 0. Give us our x-intercepts. The bottom part set equals 0. Give us our vertical asymptotes. So 3x equals 0, x equals 0. That's my x-intercept. X plus 6 equals 0, x equals negative 6. That's my vertical asymptote. So at 0, x equals 0, we have our x-intercept. At x equals negative 6, we have a vertical asymptote. We have to graph it. So what's our horizontal asymptote? What's our horizontal asymptote? Now, on the top, our leading term is 3x. On the bottom, it's x. So it's the line y equals 3. So that's my horizontal asymptote. And the last thing you would do to figure out this graph is you would pick some points and plot them. But since we know our x-intercept is here, the graph is going to look something like this. Again, you plug in some points. So plug in, we know 0 already. So we plug in -3. We plug in 3 and see whether, and we get our points. The same thing here. Plug in -9 or whatever. We'll see, we'll get these points. But you have to do some work at that point, is graph the plot. We want everything below the x-axis, not the horizontal asymptote, the x-axis. The x-axis is here. So where's the graph below the x-axis? Right here. This is part of the graph that's below the x-axis. From -6 to 0. That's the answer of that graph. The vertical asymptote will always be a parenthesis because you can't use it. The 0, the x-intercept, all depends on the inequality. Since that doesn't have an equal sign, it's going to be a parenthesis. If it had a less than equal to, then it'd be a bracket. Okay, last example. First step, we have to get equal to 0, so we have to subtract 1 from both sides. Since we're dealing with fractions, we have to have a common denominator. Right now, this one is 1/1. So we have to multiply x minus 4, x minus 4, top and bottom. Since we have a common denominator, I just worry about the top. X plus 1 minus x minus 4. Since I have a common denominator, I just worry about the top now. I don't need the first parentheses because it doesn't have anything in front of it, so it's x plus 1. This negative goes in both of those, so it changes the signs. And combine terms. x minus x cancel. 1 plus 4 is 5 over x minus 4. We have no x-intercept because there's no x on top. The vertical asymptote is at 4, x minus 4. And the horizontal asymptote is at 0. Because there's more x's on the bottom. So if we plug in some points, if we plug in 0, we get 5 over negative 4. Negative 5, 4, so it's down here. So that means we know our graph will look like this. The endpoints of the graph of these equations will always have that shape. Because of these asymptotes, it can't cross it. So if it starts here, it has to end on this side. So that's what the graph looks like. That does it for chapter 4. On Tuesday, we're going to do chapters 5 and 6, and that'll be it for the course. I won't cover anything more, but we will have time to, the week after Thanksgiving,